Hi, my name is Raya Weimer, and this is my reassessment for cell redox. First, we're going to start off with some keywords, and the first keyword is spontaneous. A spontaneous reaction occurs when a cell generates a voltage on its own, and the standard electrode potential for a redox reaction is positive. Complete reaction. The next is non-spontaneous, is when an external voltage is applied to a cell and the standard electrode potential of a redox reaction is negative. This is a non-complete reaction. The next is electrode, the solid in the half cell where electron transfer occurs and the wires attach. Electrolyte, a substance that conducts electricity when dissolved in water in an ionic solution or solutions. The next is external circuit. This is when the wires, or the voltmeter, are used to connect the anode of the cell to the cathode. Electrons flow from the anode to cathode in this circuit. The next is salt bridge, a tube filled with electrolyte solution, and it keeps the solutions electrically neutral, allowing free flow of ions from one cell to another. The next is cathode. Cathode is an electrode where reduction occurs. This is where the SOA reacts, and SOA stands for the strongest oxidizing agent. The next is an anode. This is the electrode where oxidation occurs. This is where the SRA reacts. The SRA is the strongest reducing agent. Next is a part of your internal circuit, your anion. Your anion is negative. It's a negative ion and it moves towards the anode. And then your cation, and it's positive, and it moves towards the cathode. Now, your internal circuit, anions go to the anode, and the cations go to the cathode. Electrolytes are needed for this. Next is the voltmeter. The voltmeter measures the flow of electrons using wire leads attached to the electrodes. And last, is the porous cup. A cup of pipe clay or other equivalent material used in a voltaic cell, and its job is to keep two liquids apart. It also permits electrolysis and electrolytic conduction. First, we're going to talk about electrochemical cells. An electrochemical cell is a voltaic cell. This cell spontaneously reacts to produce electricity. It converts chemical energy to electrical energy. And in a voltaic cell, you separate OA from RA, and to do that, you have an anode and a cathode. Oxidizing agents act as the bullies, and they steal electrons from the reducing agents. This type of cell requires a salt bridge. It requires a salt bridge because you need electrolytes to keep solutions electrically neutral, allowing free flow of ions from one cell to another, so when your electrons are moving from anode to cathode. The direction of ion flow goes from anions to anode and cations to cathode. And in a voltaic cell, your standard electrode potential is positive. The next cell is your electrolytic cell. This cell is an electrochemical cell that uses electricity to cause a non-spontaneous chemical change. It converts electrical energy to chemical energy, and the direction of the electron flow is anode to cathode, and the direction of the ion flow is the anions to the anode, and the cations to the cathode. A salt bridge is usually not required, and its standard electrode potential is negative. With these kind of cells, it needs a power source in order to work. Now moving on to electrochemical cell half reaction equations. Here at the top, you have your cell line notation. An example at the bottom. You have zinc solid, zinc with a positive 2 charge and is aqueous. Then you have dichromate with a negative 2 charge and is aqueous, a hydrogen with a positive charge, and carbon solid. And your hydrogen is also aqueous. So using your table on page 7, you can determine your SOA and your SRA in your cell. Looking at your table of selected standard electrode potentials, you can see that your dichromate with hydrogen is your strongest oxidation agent, your SOA, and your strongest reducing agent, your SRA, is your zinc solid. From this, you can determine your half reactions, which are dichromate plus 14 hydrogen aqueous plus 6 electrons, turning into 2 chromium plus 3 plus 7 waters. And that is your reduction reaction. And your oxidation reaction is zinc solid, which is turning into zinc 2 plus aqueous plus 2 electrons. Since your dichromate half reaction does not contain a solid electrolyte to serve as a conductor, you use carbon solid in your reduction half reaction and it acts as your cathode. The zinc solid is your electrolyte and anode. After you find your strongest OA half reaction and strongest SRA half reaction, you need to make your final equation. So what you do is you need to balance out the electrons. So in my equations, in my reduction equation, I have 6 electrons. In my oxidation equation, I only have 2 electrons. So I need to balance the electrons in order for them to cancel out. So what I need to do is deal with my oxidation equation, and I need to times that by 3 to make my electrons 6, so I can cancel out the top 6 electrons. But when I times my whole equation by 3, it also changes my zinc, which will now be 3 zinc solid and 3 zinc aqueous. After I cancel out the electrons, I need to add up the 2 equations. I need to add my reduction equation to my oxidation equation in order to get the bottom equation that is seen on my paper. Normally, redox reactions can be predicted by 1. Finding the SOA and the SRA, then 2. Multiplying the half reactions to make electrons gained equal electrons lost, and 3. Adding the half reactions together. However, in some cases, another reaction occurs that is not the one predicted. This occurs in electrolysis. Electrolysis uses a direct electric current that produces a non-spontaneous reaction in the cell, and it can result in a different reaction than the one predicted. The next thing I'm going to talk about is standard electrode potentials, or in other words, standard reduction potentials. The standard hydrogen half cell contains a solution of 1.00 moles per liter of hydrogen, and the hydrogen half cell is assigned a standard reduction potential value of 0.0 volts. This serves as either the anode or the cathode, depending on what the other half cell is. And here's a diagram of the hydrogen half cell. Your HCl serves as your electrode. The importance of the standard electrode potentials is that it is useful in determining the direction of a reaction. The next thing we're going to talk about is standard cell potential. With this equation that I have, you can find out whether your cell is spontaneous or non-spontaneous. So whether the reaction is going to go through completely or is not. So in this equation, you have your cathode and anode. Let's remember that your cathode is where reduction takes place and your SOA reacts. And your anode is where your oxidation takes place. Your SRA reacts. So after you determine your SOA and your SRA, you also know your cathode and anode from the half reactions we saw earlier. With those half reactions, you can turn to page 7 in your work booklet and find the standard electrode potentials of your half reactions. Now let's go through an example of standard cell potential. So we're going to use the half reactions we did in our first example. So for your cathode, the standard reduction potential is positive 1.23. And for your anode, the reduction potential is negative 0.76. From there, you need to go cathode minus anode. So you'll do your 1.23 positive minus your negative 0.76 to get the standard cell potential of positive 1.99. From this, you can determine that your cell is positive and is going to be a spontaneous reaction. However, if it was the opposite and your standard cell potential turned out to be negative, it means that your cell is undergoing a non-spontaneous reaction, so it is not complete. The next thing we're going to talk about, the last thing, is Faraday's law, and we're going to go through a couple symbols that you need to know for the equations. Electric current is symbolized by an I, and amperes is the rate of flow of electricity, which is current, and it will be symbolized by A. Next is coulombs. It's electric charge. It's a large number of electrons, and that will be symbolized by C. And then there's Faraday's constant, the number of coulombs per mole of electron, and that will be symbolized by an F. However, to find moles of electrons, you need to use this formula, which is F is equal to electric current times time divided by 9.65 times 10 to the power of 4 C moles, so coulombs per mole, where T stands for time in seconds. Now let's go through an example. Here we have a current of 1.50 A, and it is applied for 100 minutes to a silver nitrate solution. The question is, what mass of the silver metal could be plated on a steel bar? First, we need to get our half reaction, which is our silver. The only thing we care about is our silver metal, which will most likely be a solid. Here we have our silver positive aqueous plus electrons turning into our silver solid. And what we need to do, like our first step, is to calculate the number of moles of electrons. So what I did first was I wrote down all my symbols and what I know. However, we need to convert our 100 minutes to seconds. So here I did that, and we got 6,000 seconds. So now I think I'm ready to go to find the number of moles of electrons. Using that equation that I told you about in the last slide, you will need to go 1.50 coulombs per second times 6,000 seconds divided by 9.65 times 10 to the power of 4 coulombs per mole. And once you do that, you get your moles of electrons, which will be 0.0933 moles of electrons. However, you're not finished yet because you need to get the grams because it's asking for what mass of silver metal. So you need to get the grams of your silver metal. So this is where your stoich comes in. You will take your 0.0933 moles of electrons and times it by 1 mole of silver solid divided by 1 mole of electrons. Now, once you do that, you got it into your moles of silver. However, you still need to find your grams. So what you do is you now times your 0.0933 moles of silver solid times the grams. So your 107.87 grams divided by moles to get your mass of silver metal. It should be 10.1 grams. Now this comes to the end of my cell redox presentation. I hope you enjoyed. Bye!